was this part, right? So let's say before we even solve it, we don't know, the tension here in this part of cable is equal to the tension in this part of cable. Although last class we discussed it very briefly that if you have a cable, it doesn't matter how many pulleys you have. If it's frictionless, massless, the tension is same along one cable. But if you have a different cable, the tension may be different. But along one cable is the same. But right now, for this moment, let's assume that we are blind and we don't know it. So let's say the tension here in this part is T1, tension in this part of cable is T2. Now if I use the basic fundamental laws and prove that T1 is equal to T2, it's kind of like a proof for our concept too. So further, after this class, whenever we see a cable, there is around a bunch of pulleys, the force in that cable is same. But right now, for this just particular case, just to prove it, let's consider this one T1, T2, right? So now let's go ahead. What should I do? First of all, part A says find the force in this cable, right? Or T1. Then part B, it says find mass M, mass of this block, such that it stays at equilibrium. Well, based on your intuition, you can see that if this is a little bit heavy, right, this is going to go slide down because we don't have a friction, right? And if it's just a little bit lighter, then it's going to go this way, right? This thing is going to start going down, right? So at a particular weight, at a particular mass, this thing becomes balanced. So right now, for part B, say find M such that system becomes balanced, right? So now what should I do? Every problem I solve, I have to do a 5-step procedure. Step 1, choose your system, or systems, parentheses with S. You may have more than one system. Step 2, free body diagram. Step 3, write your equations. In this course, there are equations of equilibrium. In other courses, you just get a different equation, but the procedure is the same, right? 4, solve them, and I ask you, please first write all the equations, and then proceed to solve them. Because if you know how many equations and what type of equation you have, then you can choose which one to first solve, right? So first do all the equations and then solve them, right? 5, verify. So for example, if I get tension negative in this cable, in this step verification, I should ask, why did I get compression effect in the cable? The cable is not like a spring, it's not like a bar. It doesn't accept compression, right? So you should always go back, reiterate, and see what part of the problem you're doing wrong. It's kind of like a solution manual. It gives you some approximation for the solution, right? So let's do step 1, system. So if I only want to find, like if in the exam, I give you 1 minute, 60 seconds. And I'll just say, the question is find the force in the cable. Then what would be your system?
Just one system.
Just one system, and that is?
It's the rope and the block.
The block, this part, right? You're not interested in this part, the reaction in this pin at the center of the pulley. There are forces there, but you're not interested for the question. You're not interested in how much normal force is holding this up, right? You are only interested in tension cable. So this would be your definite choice for system. So you go ahead, choose this, right? Make a free body diagram, write the equation, solve it, verify, and you're done, right? But for the purpose of elucidation for this problem, I want to choose every single part as a system very slowly, and then draw FVD for all of them, and then do equations, right? So let's do that. Let's pick this guy as system 1. So this will be my system 1, and let's pick this pulley as system 2, and the other block with mass M as system 3, right? Now I have my systems, right? Now draw FBD. Let's start with system 1. So what should I do in order to draw FBD? What should I do in order to draw FBD?
Just the block and the rope.
Huh?
Just draw the block and the rope.
You're trying to isolate this guy from the surrounding and put the effect from the neighbors on this object. So that's the concept of free body diagram. You remember we had 2 steps. Free body diagram, you're talking about surface effect, surface effect, and body effects or forces. Surface forces, body forces, right? Now, in order to find the surface force, what do you do? What's the procedure?
Walk around.
Yeah, pick a start point like here, and then start walking around. It doesn't matter if you go the other one or this one, the clockwise or counterclockwise. It doesn't matter. Just walk through around it, right? So the first thing you caught from the surrounding, because this is your oscillation, this is your system. The first thing that communicates with this block is this cable. And you only have one force here. Sometimes when you cut it like that, you may have several force and moment components. But here you only have one force, and it's in the y direction. Do I know it? Then you ask the question, do I know it? No. So I have to define a variable because I don't know it. So let's call it T1. I already wrote it here, right? So, but you can call it X1, Y1, Z1, doesn't matter. It's just an unknown, right? So let's put here T1. And its direction is tension, is upward, right? So now go walking around it, right? You're not cutting anything from the neighbor, not cutting anything. Just then come back to the first one. So I'm done with the surface force in this system. Now I go to the body force. What are the body forces? Gravitational force.
Weight and gravity.
Gravity doesn't touch it, right? It's from invisible force, right? So what's the gravitational force on this? mg, chapter 1.
9 times or 10 times 9.81.
Which is 98.1. So again, you ask the question, do I have it or not? Yes, I do have it. So if you have it, don't introduce a new variable. Just write it down. So here, you see, if that's the center, then gravity is 98.1, which is 10 times 981, mg, right? What else? I did surface force, body force, and that's all. That's my FED. For system 1. So you write little thing here, system 1. Now let's go to system 2, right? So the system 2, you have a pulley like that, right? And then we draw a three-dimensional rod. Alright, so this is an exploded view of the pulley and this pin that goes through the pulley, right? And let's say this pin is connected to somewhere, let's say it's welded to two ends. It's welded to surface. You see that? So this is belt. So this pin is there are some bearing here, ball bearing, right? One here and one here, right? So in fact, you have two pin connection, and then this is center pin, this shaft, and this pulley goes in the center. And as you can see, this can easily rotate. Because there is another ball bearing here, right? This can easily rotate around this, and it's frictionless. You see it, assumption is frictionless. So this pulley can easily rotate. So if this cable is moving, it can easily rotate this pulley around the center shaft, right? So as you can see, this shaft is going to apply forces. So like this, two force on this, and the same thing, I put it like this. So the pulley it apply these two forces on the shaft, and the shaft apply the opposite same forces on the center of pulley. So if I choose my pulley as a system, I'm not talking about this guy. I'm talking about this guy, right? You can see there are two components of forces coming from the shaft on the pulley, right? So now, with having said that, let's go draw the free body diagram for system 2. Just to prove it. Now we're looking from here, right? So what do? Draw, find surface force, find body force. You see these two, always we do that. So what should I do in order to find the surface forces? Walk around this dash line, right? The first thing I caught is the tension in this cable. Do I have it? No, but I already introduced a variable for it. So just use this, right? So you have T1, but it's going to be opposite in direction. You see that? And then continue walking. You're not cutting anything, you're not cutting anything. The next thing you cut is this part of the cable. And for this moment, let's say just it's T2, right? We don't know yet it's equal to T1. Make this vertical. All right? Let's say it's T2. And if this is 30, then this angle is what? 30. This line is cutting these two parallel lines. So if this is 30, the other one is 30. So this angle is 30 degrees, right? Okay, continue walking. But before you come to the first point, look, you still have this connectivity. You have to figure out. So you still have to include these effects here, right? You see these two forces? The pulley applies forces on the shaft, and the shaft applies exactly the same but opposite on the pulley. So every time you want to find what force of movement you have, you ask this question. Can I move it in X? Can I move this pulley in X? On this picture, can I move this pulley in X? No. So there is a force in the X direction. There is a component there that is resisting me, and I don't know it. So I introduce a new variable because I don't know it. So I say there's going to be this guy, I'm talking about this guy. There's going to be a force Fx, and now ask the question, can I move it in the Y direction? No. So there's going to be a force in the Y direction. Fy. Can I, now talk about moment, can I move it freely around the shaft, yes. The pulley? Yeah, so there is no counter moment that resists me. There is nothing resisting against me, right? So there is no static moment here. It's only Fx, Fy, two unknowns. So these are, after we do that, we can pass this connectivity and come back to the original point, and we are done. These are surface force. Now go to body force. Do I have a body force for the pulley? It's a massless pulley, so mg is 0 almost. So we don't have body force. So that's it. That's my free body diagram for the pulley. Now let's go to system 3. for system 3, you have a mass that is a sliding, this mass, only mass, all right? This is my system, right? So I want to draw FED for that. What do I do? Step 1, find surface force. So walk around here, the first thing you cut is the tension in this cable. What's the tension in this cable? I don't know, but I already introduced T2 for that, right? So I put T2 right here, T2, right? And then continue working, so not cutting anything, and then you come to this contact point. This is a contact point, right? And if it's frictionless, there is only a force that keeping it this way. There is no friction force against the direction of motion. There is only a vertical force. So there's going to be a force, and since I don't know it, I put a new variable, n. I don't know it, just call it n. You can call it x, y, whatever you like. Just a variable unknown, right? And then I come back to the original point, and I'm done with the surface force. Now what am I missing? Body force. So what's the body force?
Gravity on the mass.
Exactly, mg. Do I know the gravity, the mass?
No.
No. So I just use mg, right? So what's the direction of it? It's just vertical, right? mg, and I don't know it, right? Now let's go to some angle computation. If this is 30, this is normal to that, right? If this is 30, in this triangle, if you consider this guy, this triangle, if this is 30, this is 90, this is 60, right? Now go to this triangle, right? The bigger one. So this is 90, 60, so this angle is 30. That means this angle is 30 degrees. Okay, now I'm done. This is my FED, right? Now let's go ahead. So I'm going to go and check mark FED, right? Now let's go ahead. Step 3, write the equation. So let's first write all the equations, right? So for system 1, these are the equations. System 1. Summation of force, let's say this is your x, this is your y. Look, this xy, this is like choosing the system. It's not given to you. You choose where is my x, where is my y. But whatever you choose, it should be consistent with the right hand. That means if you take your x here, y here, z should be here, if you're solving a 3D problem, right? So right now I take x, y here, but look, I can take x, y right here. You can rotate it, you see? I just rotate it and I align it with this in order to simplify the equation, because if you don't rotate it, still you can solve it, but the equation becomes coupled. It's a little bit lengthier than doing this way. Later on, when you practice, you learn all the tricks, right? But still, if you choose the same x, y, you can solve all the problems. It doesn't matter, actually. This just makes your job a little bit easier. And for this guy, put your x, y here. So what I'm trying to say is you choose the x, y. You are the person that chooses everything, right? Okay, now system 1, summation of force in x is what? Resultant force in x. And we said, according to Newton's law, resultant force is 0 as long as the object is in equilibrium. And the question is, find the value of m such that this is in equilibrium, it's not moving. So we can use that, right? So resultant moment in x, summation of force in x, resultant force in x. What should I write? Resultant force in x.
No, it's not going to
It's going to be no. Because you guys, you see that we don't have anything in the x. You see? So 0, which is summation of force in the x, is just 0, right? According to Newton's law, is 0. This comes from Newton's law, summation of force in the x. So 0 is equal to 0. So it's a null equation, right? I don't even want to write it. when you practice, learn to avoid extra computation, extra writing, right? You always want to make a shortcut as an engineer. So I just go ahead and write summation of force in y direction. What's the summation of force in y direction? T1 minus 98.1 is equal to 0. How about the moment equation? Summation of moments. Let's pick this point as a moment. What do I get? Moment from this. What's the moment from this with respect to this one? 0. What's the moment from this with respect to this one? 0. So 0 is equal to 0 is a null. I don't write it. So the only equation is get is this guy. And I'll just label it equation number 1. Right? Now let's go to my system number 2. I need to write, this is sys2, and this guy is system 3, right? Now let's go to system 2 and write equation. Summation of force in the x component is 0. So what do I get? T2 cosine 30 negative fx is equal to 0. Summation of force in y, 0. That's going to be T2 sine 30 negative fy negative T1 is equal to 0, and summation of moment around the center O is 0. So let's work on this last equation together. So if I want to find the moment with respect to O, let's start with fx. What's the moment of fx with respect to the center? 0, going through the center. What about F5? 0, right? So the only thing that remains is T1 and T2, right? So what's the moment of T1 with respect to the center? Let's say this radius is R. The radius of this pulley is R, here. This radius is R, right? And I don't know it. I didn't give it to you in question. It's arbitrary R. Doesn't matter, right? So what is the moment coming from T1 with respect to the center? T1R. Positive T1R. Now we go to the last one. This guy is normal to this distance. So what's the moment coming from T2? What's the moment coming from T2 with respect to this center? R times T2R, right? Positive or negative? Negative. Negative T2R. And these two guys, the moment is 0. It's going to the center. The moment is 0. So I'm done. Summation of moment according to Newton's law is what? Is 0. Right? So you can immediately see, look at here, guys. What do you understand from this equation? T1 is equal to T2. So even though if we assume that we don't know this fact that the force is constant along this cable, no matter how many pulley we have, as long as no friction, no banks. Even though if we don't know it, you can still prove it using basic fundamental Newton law of equilibrium, right? So that is exactly what I mentioned last guy. This is a proof for that, right? Now let's number this equation number 2, equation number 3, equation number 4. Now let's go to my final system. This guy, right? Here I write equation for this here. System 3. Now my axis x positive is this way. So what's the summation of forces in the x positive? Let's start with this guy. What's the component of this in the x positive? Only sine 30? mg. Yeah, mg sine 30. Right? Positive or negative? Positive. Now let's go to this guy. If this is your x and this is your y, does it have a component in the x direction? If this is your x, this is your y. No, this is purely in y, right? So skip it, because we're doing the x business. We're doing everything with x, right? Now go to this guy. What do I get? Positive or negative? Negative. T2 is equal to 0. Summation of force in the y direction is 0. Again, you get negative mg cosine 30 plus n is equal to 0. What about moment? Let's say this is my reference point. What happens for moment? All the forces are going through this, they cancel, so it's a null equation. It's not useful at all. The moment equation is only useful when not all forces going through one point. Then you can get that to get extra information to solve the problem. Now I'm done. The step number 3, let's check mark it. You see that? Now I go to solve the equation. Now I can see the entire picture. Now I ask you, what part should I start first? What equation should I start first to solve? System 1, equation 1. Here in this very simple problem, the order of equation accidentally matches with the label of equation. But when we go to the frame, you may start with equation 4, or 12, or 16. We're going to get a lot of equations. You will be amazed how many equations we get. So you should first have all the equations and see which one is one equation, one unknown, decouple. So you can solve that and get the value, substitute in another equation, and solve for everything. So let's solve equation 1. And this is the answer to part A of the quiz. So T1, let's write it back. T1 is equal to 98.1 Newton. 3 significant digits. That's what I get, right? Now what is my next step? Equation number 4. Equation 4. So the first step is equation 1. And the second step is equation 4.
Why do we have to do 4?
Huh?
Why? Why are we doing 4?
Because if you want to do this guy,
Because you need T2.
you need T2.
Yeah.
And let's say you are kind of blind. You can't just see this. Here I have T1, right? Not T2, right? So I have to connect T1 to T2 and then use it to solve for all these guys, right? So if I solve this, look, this R cancel out and T1 is T2. So that means T2 is 98.1 Newton, right? So what is my next step? The answer is, it depends on what question is asking for. Don't waste your time. If you solve 2 and 3, yes, you can do that. You see, you have T2 multiplied this by cosine 30. You get the X component of reaction on the beam, on this shaft. The external reaction. But this is not what the quiz is asking for. So skip it. Skip these two guys. You don't need Fx, Fy, although you can solve for that right now, right? Now, what is my next equation I should solve? Let's say this is equation 5, and this is equation 6. So which one should I solve?
5, because you got T2.
5. So now, equation 5, if I solve it, I get what? The unknown mass, which is the answer to part B of the question. So let's solve equation 5. So if you solve equation 5 for m, then you get m is equal to M is equal to, take T2 to the right, over G sine 30. You see that? I solve for M. T2 over G sine 30. Just substitute the value. What's the T2? 98.1 divided by G 9.81 times sine 30. Half. Right? So 98.1 divided by 981 is 10. Right? Multiply by 2, the end result 20. So the mass is, this mass is 20 kilogram. The answer to part B. Mass is 20 kilogram. If you have a little bit higher than this, it's going to slide down because you don't have a friction. If you have a friction, you may get a range. This is an interesting thing. If you have a frictional effect, we're going to discuss friction soon. You get a range. It could be probably 21, 22, or some range. But because you don't have friction, the moment you make this mass 20.001, if you add 1 gram, it's going to slide down. And if you get 19.999, you remove 1 gram, then it's going to go up like that. This is going down. So you get the exact value. But look, in the actual physics, it's not like that. You can add a little bit more weight, and it still is not sliding, right? Because of friction. So you can find the range. All right. Now I want to close it today and next class before we actually go home.